Penetration depth, or PD, is the minimum amount of transformation required to separate two intersecting objects. It is an important component of many simulation algorithms. Here we show a complex simulation in Box 2D with a high number of characters. The simulation uses our algorithm to efficiently compute the penetration depth between these non-convex characters, as shown in the zoomed-in video. Here is an example of a complex 3D simulation. Both upper and lower teeth consist of 40,000 triangles. The complex shapes lead to many simultaneous isolated contact points. Computing PD in such scenarios is very challenging. There are two types of penetration depth. Translational PD only considers translational motion to separate the intersecting objects. Generalized PD considers both translational and rotational transformations. Penetration depth plays an important role in dynamic simulation, geometric modeling, haptics, robotics, motion planning, and interactive applications such as games. Local techniques compute PD for each contact independently, but they can have difficulties with multiple simultaneous contacts. Global techniques consider all contact points. However, these techniques are usually too expensive for interactive applications. Interactive applications tend to utilize efficient local techniques. However, these techniques may produce a set of contradictory solutions for non-convex shapes with multiple contacts. This 2D simulation shows the benefit of global PD over local PD. Global techniques can successfully separate these complex objects. We present a novel approach for computing global penetration depth which uses learning techniques to approximate the contact space of two objects, called learned contact space. The 2D generalized penetration depth creates a 3D contact space. This sequence shows the final learned contact space and a sequence of previous refinement iterations. The active learning technique takes an iterative approach to defining the contact space. Each iteration samples the configuration space through the principles of exploration and exploitation. These samples are then used to refine the approximation. The refinement ends when the approximation satisfies certain error-based conditions. Here we illustrate the learned contact space using two non-convex objects, a cup and a spoon. This shows the evolution of the approximate contact space between the cup and spoon for translational PD. Beginning with the initial approximation, successive iterations of the active learning algorithm shows that the approximation quickly converges towards the actual contact space. The left video shows penetration. The right video shows the collision-free motion created by using our generalized penetration depth computation. We show the result for various spoon trajectories. Here we highlight the performance on a complex simulation in Box 2D. We use more than 1,000 birds and 50 pig characters. In this complex simulation, we use our PD algorithm to compute a measure of penetration between overlapping pairs. Box 2D uses a collision response based on penetration depth. The average PD query takes 0.15 milliseconds for each overlapping pair. Our approach can easily handle non-convex objects in such complex situations. Next, we show the results on a complex 2D spider model used in Box 2D. There are multiple contacts between the non-convex spiders, including some deep penetrations. Our algorithm takes less than 0.1 millisecond for each pair of overlapping spiders. We've also incorporated our algorithm in the Bullet physics engine to use with 3D rigid models. Here we show the collisions between 10 interlocking rings in this chain. The PD query takes less than 1 millisecond for each pair of overlapping rings. Here is a stack of more than 1,000 rings falling on each other, resulting in multiple contacts and penetrations. We compute generalized penetration depth between each pair. In this simulation, a tower is built of 5,500 rings. As the tower collapses, we see a high number of penetrations and contacts. We have presented a simple algorithm to reliably compute global PD between non-convex objects. It is more than an order of magnitude faster than previous approaches, allowing for interactive applications.